Okay, great. So thank you everyone for joining us for this week's SAME seminar. This week we have Faizyab Chaudhary at the University of Alabama in Birmingham that's going to be talking about lung function and generative AI. He just graduated from Reinhardt's lab at University of Iowa, and just this June he started his position as an instructor at the University of Alabama in Birmingham. So thank you, Faizyab, for giving this talk, and take it away.
Thank you so much, Jorge. Can you listen? Can you listen?
We can hear, yeah.
Okay, perfect. Okay. Hi everyone. Thank you so much, Jorge, for having me here today. I'm Faizyab, as you can see my name here. I'm currently an instructor at the UAB School of Medicine, where I joined this June. Before that, I was a PhD student at Professor Reinhardt's lab in the Roy J. Carver Department of Biomedical Engineering. The work that I'll be presenting today was done at Iowa. So without further ado, let's start. So I think let me highlight my brief career trajectory. So I was born in Lahore, where I did my undergraduate degree, a Bachelor's of Science in Electrical and Computer Engineering from UET Lahore. Lahore is a very multicultural kind of a city, just like Iowa City. It's like a city of literature, and this is the Grand Mosque that we have here. A lot of people every year visit this mosque, and after my undergraduate degree, I came here at the University of Iowa for a PhD, where I graduated in 2024, which is earlier this year. This is the old Capitol building that we have in Iowa, really beautiful quad, and now this is a part of our campus. At Soon after graduating from my PhD, I moved to the University of Alabama at Birmingham School of Medicine, where now I'm an instructor and the Division of Pulmonary, Allergy, and Critical Care Medicine. This is, again, the quad for the UAB. To briefly give you an overview of my mentors, so these are all my mentors and collaborators who have helped me a lot during the year. This is Professor Reinhardt, who have helped me immensely. He was my PhD supervisor. I was co-advised by Dr. Eric Hoffman. So Dr. Eric Hoffman is a well-known imaging-based pulmonary physiologist. He has done his early career was based on pulmonary physiology. Then he moved to imaging, and he has done a lot of work. And then another of my mentors is Dr. Sarah Gerard, whom I did a small postdoc with before joining here. So she also, I have learned a lot from him. We have at UAB, I have Professor Surya Bhatt, who I work with, and Sandeep Bodaluri. Here you can see Dr. Sean Fain. Dr. Sean Fain just joined Iowa. He is one of the few experts in the US who use hyperpolarized gas MRI scans for understanding the functional lung image components. So yeah, and at the UAB Hearsing School of Medicine, the two of my mentors, they just recently constructed and got approved for a center, which we are calling as the Center for Lung Analytics and Imaging Research. And I'm part of this center. We are trying to basically gather multimodal patient data for future analysis. And another very interesting thing is that both Iowa and UAB, they are part of two large multi-center clinical studies targeted at understanding COPD, which is a lung disease, the chronic obstructive pulmonary disease. SPIROMICS is being conducted on, I think, 14 clinical centers, and COPDGene is being conducted at 21 clinical centers across the United States. While the centers overlap, the patient cohorts don't. And thus we have a lot of patient data imaging and multimodal data, like you can get blood biomarker data from all of these cohort studies. And I have been fortunate to be a part of it, and have used the data throughout my PhD and still using it. Without further ado, let's talk about COPD, which is a very complex disorder. It manifests in two different ways. Either it could damage your airways or the lung parenchyma, and it could be both. And it could lead to severe difficulty in breathing, shortness of breath, and severe cough, which may sometimes also lead to a hospitalization, which eventually causes a very severe decline in lung function. So local lung disease patterns, as we know, are very heterogeneous, not just in COPD, but if we look at the lung of an interstitial lung disease patient, you can see these honeycombing and ground glassing textures. Basically, it's the scarring that has spread across the entire lung. Similarly, if you look at COPD, you can see this large blob of emphysema, which is basically air. The tissue has basically been destroyed and emptied out here. For cancer, we all know we see some lung nodules, right? Now, these chest CT scans are widely acquired in the clinic. And an important technique that I'm going to introduce to analyze chest CT scans is image registration. And it has a very close connection to lung function, and I'll talk about it. So, image registration and lung function. Okay, the first thing that I'll be talking about is the local tissue expansion of the lungs, which is also called the Jacobian. Let's see what it is. You can see here an end inspiration scan. So whenever a patient comes in, this is the most common type of chest computed tomography scan that's acquired. The patient lies down in the bed and they're asked to basically inhale to the max, and a chest CT is acquired. Now, this is prescribed in almost every clinical setting where a chest CT is acquired. Now, SPIROMICS and COPDGene and some clinical settings often also acquire an end expiration scan, where you basically ask your patient to not only inhale, then you ask them to exhale as hard as they can, stay there, and then they acquire another scan. Now, looking at these two images individually, they are structural. They basically provide you structural information, right? And a radiologist or a pulmonologist will have to look at them to basically identify what's wrong and what could go wrong, what could possibly go wrong, right? And these two images are not inherently functional. Are these functional? No, they're not. So what Reinhardt et al. Did in 2008 is they used image registration to basically match these two scans into the same space. Typically, inspiratory image is matched with the expiratory image, which is from the larger volume to the smaller volume. And then they derived a spatial, by analyzing that deformation field, they derived a Jacobian determinant, which gives you a measure of local tissue expansion of the lungs. Local tissue to give you, and some other measures which we can ignore are the emphysema and the air trapping. So to give you a little bit more introduction on Jacobians, so you can see here is an FRC, or the functional residual capacity image. We also call it an expiratory image. So in an expiratory image, you can clearly see the lung is smaller. In an inspiratory image, or the total lung capacity image, the lungs are inflated. And by analyzing this displacement field, you can get the Jacobians in both of these spaces. In expiratory space, it will tell you about the expansion. In the inspiratory space, it will tell you about the contraction. Now, another very important image registration-based approach for analyzing lung disease spatially is the parametric response mapping. It also relies on image registration. Basically, what they do is they register the inspiratory and expiratory images into the same space, and then they construct this 2D histogram. Based on this 2D histogram, they basically define two different thresholds to characterize the entire lung into three different regions. The region in green is the normal lung tissue with a higher lung density. You can see the thick tissue operating normally, right? So they call it normals. The red is emphysema, or the air. So where the lung is, so there are air pockets in the lung that are not wanted, just as I showed you a couple of slides ago. Then this approach was used to identify a novel subtype of lung tissue, which was functional small airways disease, and it's known to precede emphysema. So both of these, the Jacobian and the parametric response mapping, have been very widely used in the clinic. Local tissue expansion was associated with lung function, exercise capacity, patient quality of life. It was validated against a functional imaging modality, the xenon enhanced CT. It has been used to detect and stage COPD, and it was also associated with another functional imaging modality called the hyperpolarized gas MRI. So PRM, both parametric response mapping and local tissue expansion, have found their way into the literature. They have been applied across cohorts that have multiple CT scans, right? But now let's having said that, let's ask ourselves a few questions, right? There are a few limitations. The first primary limitation is registration-based multiple volume measures require at least 2 different CT scans, right? What if a patient is unable to hold their breath for a second scan, right? And you're not able to acquire a second scan. What if for a screening study, like the National Lung Screening Trial, right? There is only one scan that is protocoled and due to those limitations, right? What about the large multi-cohort studies that have acquired CT scans at single volume? And what about the increased cost associated with the multiple CT volumes? And another thing is that most pulmonary image registration methods incur large computational cost, and they don't guarantee diffeomorphic transformations. So we hypothesized in this study that, okay, we can use deep generative modeling to directly estimate these measures from a single chest CT at inspiration using generative adversarial learning methods. So the idea was, instead of going down this pathway where you use 2 images and then you register them to get the Jacobians, why not train a generative adversarial network directly from an inspiration to the GAN, or directly generate an end expiratory scan from an end inspiratory scan, and then get the pulmonary parametric response mapping, spatial distribution of the disease. Now, the work I'll be presenting today, it will be about generating the end inspiration to end expiration. And for that, we used the SPIROMICS data set for training and validation. Here is the distribution of the training and testing data sets across different gold stages. Gold stages are a measure of defining COPD severity. Gold 0 are typically called the asymptomatic smokers. They have no symptoms, but since they have been smoking for more than 20 pack years, they are included in gold 0. And from gold 1 to 4, the disease goes from mild to severe. Okay, a little introduction on the GANs. GANs, for those of you who don't know it, are a 2-part convolutional models that basically use a generator and a discriminator. I like to define it as a competition between a detective and a forger who's trying to forge a Monet. Now, as these 2 models train together, both of these models, or the detective and the forger, they basically start fighting with each other. And the eventual goal for the generator is to fool the discriminator so that it is unable to recognize if it's a real Monet or a fake Monet. Now, GANs have been widely used in many applications for doodling, for creating sketches, but of course, they have some limitations. They suffer from training instabilities. They can fail to generate diverse images. They can collapse, they can collapse into generating a single image over and over again. And then the instabilities are further aggravated when we try to scale the GANs to large 3D volumes. So this was a challenge. All the SPIROMICS and COPDGene data sets were acquired at a very high resolution. And to scale the GANs was an important factor of our study. And of course, you don't have infinite amount of GPU memory, which aggravates the things a little bit more. So today I'll be talking about the lung vision transformer architecture that I presented. There is a lot going on in this figure. Let's break it down piece by piece. So first, I would want you to focus on this part, which is basically the pre-processing. So we have an inspiratory scan, and then we have an RV scan, which is the expiratory scan. What we do is we first put both of these images into the same space and mask out the lung regions. So you can see after registration, we have the deformed RV. So basically for this case, RV has been deformed into the TLC space. Now you have this TLC image, which looks darker. And this is the RV image, which is in the same space, but looks a lot brighter because it has the intensities of an expiratory image. Now, this is the framework. This is the 3-part framework that I would like to describe today. So the first thing that I'll talk about is the adversarial loss. This is what makes this a generative adversarial approach. So the adversarial loss is nothing but a feedback from the generator, right? It's a 2-part system. So we have a discriminator that's evaluating the model predictions. Now, in addition to doing that, the discriminator objective is to basically distinguish what a real image is and what a fake image is. And the job of the generator is to basically fool the discriminator, right? So during training, we show them both. We show real images to the discriminator and fake. And the loss that is basically fed back to the generator is that encourages that you have to gain maximum score from the discriminator for a fake image. So basically, this is the adversarial feedback provided to the generator by the discriminator. And this is the very commonly used least squares formulation of the adversarial loss. It has been used multiple times in the literature, and it is known to be a very stable trainer of the generative adversarial networks. So moving on to the second component, we have this encoder and decoder architecture. And to explain that, before explaining that, I would like to highlight a very small component. So with our networks, we basically used deep supervision. So just like when you're training any convolutional neural network, you optimize the output from the final layer, right? But we always have that option of optimizing output from the multiple layers at multiple resolutions. So that's a small adjustment that we did to our network to basically deeply supervise our network, and it helped us improve our performance. Let's talk about this network architecture that we proposed. Okay, so a little background on convolutional neural networks. So convolutional neural networks, no matter how deeply stacked they are inherently local, which means that they process images in local neighborhoods. The problem with this approach is that if you have to, let's say you have these two patches, right, and you have to model the context between these two, you won't be able to do that because these local neighborhoods won't be captured in synergy so that the network can make a decision. So that's one of the pertinent limitations of convolutional neural networks. Now, so the answer to the question, if the neural networks, the convnets can learn the relationship between distant but related regions, not so much. They struggle. And that's why self-attention for learning long-range dependencies was proposed in the first place. Let me just give you a very brief insight into the long-range dependencies and self-attention. So let's look at this sentence. The quick brown fox jumps over the lazy dog. If I look at the sentence, like just the first half, the quick brown fox, we don't know over what it jumped. Basically, it could have jumped over a mountain or over a car or anything, right? But that's what convnets do, right? But the way self-attention treats it, you break this sentence into into words, and then you learn some embeddings of these words. Embeddings are nothing but learned features of the sentence. Then it's basically you construct a correlation matrix kind of an tensor, which basically use the scaled dot products between every feature. So basically, here is the sentence: the quick brown fox jumps over the lazy dog. The quick brown fox jumps over the lazy dog. These are two different embeddings. And just like a correlation matrix, you are basically learning the features between them and doing a softmax to turn them into probability distributions. Now, you set a threshold and basically you pick up the relationships. It will be a continuous relationship, and basically it will upweight the relationships that are most important to make sense of the entire sentence. So it is quite possible that the quick part is highly correlated with the lazy dog part. So you will see some high probabilities here. And the output, of course, is a map that basically gives you an importance. So self-attention, subtly, like put in simple words, is nothing but a way of learning weighted attention or a weighted averaging scheme on your features, just to know that what part of the image is important. And since it's taking into account the entire image or the entire sentence, you can basically model those relationships between two distant sentences that we were not able to do so. This is exactly how the vision transformers were were made. When you have an image, you basically split them into small patches, which are the words. In this case, you compute the embeddings, you add the position, and then basically you compute the self-attention. Now this self-attention, this transformer encoder uses multiple self-attention blocks to basically do a then you can do classification or synthesis or anything. And this is what we proposed, Swinseer architecture. Swinseer architecture uses a transformer, a vision transformer based encoder and a convolutional decoder. This is very similar to the commonly used swing unit architecture. So this is one of the hybrid architectures that are used where they have a vision transformer encoders and convolutional decoders. This is a very common paradigm. What we did is we thought to ourselves that, okay, the encoder block has swing transformer attention, right? But the convolutional block doesn't have it. So we basically inserted the squeeze and excitation blocks that would model the attention between different feature maps within the encoder, within the decoder block. And hence, we made Swinseer architecture. Without going into more details, if you have any questions, we can address them later. I'd like to move on to the third component, which was another very important component, which was called the multi-view texture similarity loss. So we know that texture in a CT is very important when translating from a TLC to FRC or RV or inspiratory expiratory image. The texture is very important. To preserve texture, a very commonly used approach is to use a VGG model and basically compute a perceptual loss function by extracting the feature maps from the layer. So the way it works is, let's say you have a slice S that's a real CT slice that you want to generate, and let's say this is the S hat which has been predicted by your network. So basically, you pass it through a pre-trained VGG, you compute some feature embeddings, and then you compute a loss function out of it. So this is the very commonly used perceptual loss function. What we did is instead is, like, instead of directly computing the mean squared error or mean squared error or any L1 loss function on these embeddings, we use the formulation proposed by Ding et al., where they use these embeddings to capture both the texture and the structural component. So if you take the structural similarity between the means, it will describe the local tissue texture. And if you look at the standard deviations, it would describe the local tissue structure. So this small variation on the perceptual loss helped us to construct this distance loss between two slices. And the slice could be a coronal slice or an axial slice or a sagittal slice. Now, for this study, we extended this loss function to 3 different slices called we did it basically so because VGG is a 2D pre-trained model, so we did it for the axial direction, for coronal direction, and for sagittal direction to come up with the multi-view distance loss function. So this all 3 of these loss functions were basically combined together to give a joint feedback to the generator. The last thing, but not the least, was a simple cascading of different lung width models. We propose a cascade. You can do N cascading to basically iteratively refine the training schemes. The weights were not shared. Basically, we trained multiple lung width models in a sequence, but at every stage, the previous model was frozen. So which we basically call it ensemble cascading. Now let's discuss some of the results. So the input to our networks was a TLC CT image. It was a 3D image. I'm showing you 2D cross-sectional slices. So this slide is about comparison with 2D models. So if you look at and this was the expected output from the network. Now, and the difference images are shown here. Now, we compared the performance of our model with pixel to pixel, Yang, self-attention GAN, pyramidal transformer networks in 2D. Then we also compared our performance with some 3D models, which was the voxel to voxel, the 3D unit RGAN, the 3D swing unit RGAN, and then comes the lung width and the lung width ensemble cascading. Now, since these 2D models, if I switch back to this slide, were trained on these coronal slices, you don't see any discontinuities, right? But if I move to the axial slice, you'll start seeing these slice-wise discontinuities in these 2D models, right? So which were of course not present in the 3D models, but still the voxel to voxel model did not converge well and had an error. And then all of these models did a good job in 3D, which we'll compare further. Now, the lung width indicates the lung width model as it is, and the lung width ensemble cascading indicates an ensemble cascade of lung width models using two different lung width frameworks. Now, we also compared the performance of our model across the different gold stages. So again, this is the input to our model, which is the TLC image. Output is the RV image. This was the RV image predicted by our lung width model, and these are the difference images. So you can clearly see that the network was also able to pick up these subtle vessel structures, which are, of course, very important for basically any analysis. And the network was able to predict across all different gold stages, from asymptomatic smokers all the way to gold 4, which was the severe most disease. We also did a bland Altman analysis between the means of the predicted images. The analysis showed a fair agreement between the image intensities, the mean image intensities of the two images. And we also did a bland Altman analysis for the clinical biomarkers. Now, I would like to again bring your attention towards the parametric response mapping based functional small airways disease. So after we trained our model, we generated the CT scans, we thought, okay, let's try to generate some functional small airways disease metrics from the synthetic images. So that's what we did here. The mean, so this is the plot, the bland Altman plot for the functional small airways disease, and this is for another RV image-based imaging biomarker called air trapping. So the overall bias was minimal, 2% in this case and almost 1% in this case. There were some outliers, which we have now investigated. And overall, the model performance was good. There was no obvious systematic presence of outliers. And similarly, so this was for the lung width. If we move on to the lung width ensemble cascading, it basically tightened the bounds a little and decreased the bias from 2% to almost 0.92%. And another very important part of our study was to look at the estimated functional small airways disease and air trapping across different COPD gold stage severities. And that's what we did here. You can see as the disease progresses, the functional small airways disease shown on the RV images, the actual RV images, which have been acquired through the clinic, go up. The GAN picks up the same pattern in both cases and is able to describe the disease without requiring a second RV scan at inference. So with this, we were basically able to demonstrate that, okay, once trained on TLC and RV pairs or inspiratory-expiratory pairs, the images can be used to characterize and phenotype patients into different disease severities. We also compared our method using various quantitative metrics with all those different methods that I showed qualitatively, and our method demonstrated a significantly higher performance against all of these methods. Now, another important part of this study was to see if it generalizes to an out of distribution cohort. So we did an out of distribution or an external evaluation. So the models were trained on SPIROMICS cohort. Then we applied them to almost 500 subjects from the COPDGene cohort. Again, the model showed reliable performance. The AUCs and not the AUCs, the PSNRs and the multi-scale structural similarities were the same were about the same for the lung width model in both the cohorts, and they performed better than all the other different 2D and 3D methods. to conclude, this was one of the first studies that looked at the problem of cross-volume image synthesis. And the study was published earlier this year in IEEE TMI. You can read the paper. It's available online. So this was basically the first local surrogate of lung function that we developed using just the single TLC CT scan. Another very small part of my study that I would like to squeeze into my presentation is the generation of pulmonary ventilation imaging, or the hyperpolarized gas MRI, that too from the TLC scan. So this is a preliminary study that we conducted, and we used the very basic pixel to pixel 2D framework because the resolution of the hyperpolarized gas MRIs are very small, is very low. So gas MRI is a functional MRI that basically asks the patients to inhale a hyperpolarized gas. It could be xenon or helium, and then they basically scan it through an MRI, and then it gives you this very nice distribution of ventilation across the entire lung, and you can see the regions where there are some ventilation defects. So this was a preliminary study. We used data from the Severe Asthma Research Program, and which acquired inspiratory CT volumes and hyperpolarized gas MRI scans for understanding asthma. And we used almost 59 CT and MR volume pairs. To look at the results, these are some preliminary results. Our GAN generated a little over smoothed image, I would say, because the data set is very small, the network is not as sophisticated, and the gas MRI itself is a little noisy. So all these factors contributed to that. But overall, if you can see with through the arrows highlighted, the network was able to capture some of these regions with the ventilation defect. Now, here is some quantitative analysis, some Bland-Altman analysis on the means. Pixel to pixel did a fair job with a high structure similarity was good, 0.85, but still there is a lot, as shown by the Bland-Altman plots, there is a lot of room for improvement. So putting it all together, the generative models, we are demonstrating that they can be used as a measure, as a method to basically derive these regional surrogates of lung function, and this would allow for a broader impact of these functional measures to populations where CT scans were not acquired at expiration, right? And you can train these models the other way around and basically analyze subjects where the TLC scans had some problem or the TLC scans were missing. So it can basically work both ways. So that's the idea. I would like to acknowledge NIH, SPIROMICS, COPDGene for providing the data, and it wouldn't have been possible. And the Roy J. Carver Charitable Trust, who funded my PhD as a fellowship. And yes, I think that's all from my side. Thank you so much again, everyone, for having me. If you have any questions, I would love to answer them. Thank you.
Let's thank Faizyab one last time, and we have plenty of time for questions. You can go ahead and type it in the chat or unmute as well.